let's now discuss what's called one of the most famous or most important methods for stability analysis. Remember that we have something that's called the lax equivalence theorem that we discussed last class that tells us that once we have verified that a scheme is consistent, that is, consistent means that it tends to the original equation as the steps in time and space tend to zero. Once we've verified that it's consistent, then all we have left to do is to establish stability. And that ensures us that then that we get convergence, and therefore the method is a good method. So most methods for stability analysis, so stability analysis actually can become quite complicated, but there are a lot of approaches. Most of them actually rely on the assumption that the equation is linear, which is a limitation of particular importance for the Navier-Stokes equations, but unfortunately it gets very complicated if we have nonlinearity. So most methods are restricted to linear problems, and even so they can get quite complex if we want to include boundaries, for example. Normally we even want them to disregard all effects of boundaries. So, for example, one way to disregard effects of boundaries would be to consider infinite problems or to consider periodic problems. And the von Neumann stability analysis approaches this by dealing with periodic problems. So the key to the von Neumann stability analysis is to expand the solution or the error in a finite Fourier series. That's the key. Here's Mr. von Neumann right next to one of the first electronic computers, ENIAC I think it is. I'm going to dig up some biography and put it on Blackboard for you to learn a little bit more about this guy who's called by many people the father of the modern computer. And he had many contributions. One of his most famous contributions in numerical analysis is the von Neumann stability analysis. So again, we're going to use the same notation, which is that U bar Ni is the exact solution of the difference equation. Or the numerical scheme. And U without the bar is the actual computed solution at the mesh point I and the time step n. And they don't necessarily are the same because the differences could be for a round of error. It could be errors in the initial condition, etc. This can make this two different. So U Ni is going to be equal to U bar Ni plus some error, let's call it the error at grid point I and time step n. Now, of course, by definition, U bar satisfies exactly the numerical scheme, so n of U bar Ni is equal to 0, exactly equal to 0. And so let's apply the operator n to the equation above, this equation here. And we're going to get n U and I is equal to n of u bar ni plus the error. Now we assume that the numerical scheme is linear. Then this is equal to n u bar ni plus n of the error. And of course this is 0 by definition, and so this is equal to n of the error. Which means that if the numerical scheme is n u n I equals 0, that's our numerical scheme. This represents a linear numerical scheme. Then the errors satisfy the same equation as the numerical solution. This means that we can analyze the stability either by studying the behavior of the errors or studying the behavior of the solution itself. Either one is okay because they both satisfy the same equation, and so the von Neumann method chooses to use the solution. There are many other methods that choose to use instead the error, but you can see that it's about the same. So let's consider as an example, consider a 1D domain, 0L, 0, L, and reflect it onto minus L0 to create 2L periodicity. So suppose that we have some sort of, say, function here between 0 and L. This is our domain of where we want to work, and we're just going to reflect it. It should be a reflection here, but my drawing skills are not very good in this. Okay, that's better. I reflect it like that to create, reflected anti-symmetrically to create a periodic solution. Okay? So now we're going to create mesh points here and in the whole domain, right, to discretize the solution. And we note the following, that if we create mesh points, with a spacing delta x, then the shortest resolvable wavelength is going to be lambda minimum equals 2 delta x, because if this is delta x and I have a periodic solution here, then I need 2 delta x to have a full wavelength. Because if I try to put that in 1 delta x, then I would need a point in the middle, so I'm stuck, right? So you can see here, there's a tiny little wavelength here drawn in this, 2 delta x. So the maximum wave number that we can resolve, k max is equal to, well, 2 pi over lambda, and lambda is 2 delta x, so that's pi over delta x. Okay. So we have our maximum wave number, our minimum wavelength, maximum wave number. Now we can look at the largest, of course, the largest wave number is the whole domain. Well, actually, I mean wavelength, much largest wavelength that we can resolve is 2L, the whole domain. And so that means that the minimum wave number K min is equal to pi over L. So now we're looking at the discretized version of this 1D domain. So we're going to have a mesh index that goes from I equal to 0 all the way to n. So our points are xi equal to I delta x, and delta x is equal to L over n. So this is just one side, just the actual domain from 0 to L. So we want to represent now the Fourier series. So all of the harmonics of this Fourier series that we can actually represent in this finite mesh are Kj equals to J K min, which is equal to J pi over L, or J pi over n delta x, with J going from 0 to n. So we have n harmonics. We include J equals 0 for a constant solution, if there was possibility of a constant solution. And so here we have all the possibilities of the harmonics that can be represented in this finite mesh, and we define a phase angle phi as Kj delta x, or J pi over n. So this, now we're going to cover the domain. Actually, this is the whole domain. The domain for the phase angle goes between minus pi and pi, and we have steps of pi over n for the phase angle. So now we can write the decomposition in a finite Fourier series. For the solution uin, and that's going to be equal to the sum j equals minus n to n, and I'm going to use capital V for the amplitude of each harmonic, and I use the same indices n and well, j in this case for time. And the exponential, because I'm using I for the index, I can't use I for square root of -1, so I'm going to use capital I to indicate the square root of -1, our imaginary number. So e to the capital I, kj, and xi, which is also equal to sum from j equals -n to n of v and j, and I'm going to write e to the imaginary number capital I, kj, I delta x, or finally I can write it again as sum, I'm going to skip that detail there, and oh, I don't know, I'm not going to have space for that, so let's just, well, again, I can write this guy as E, I, j, the indices, and I have pi over n. Okay, so I delta x I've rewritten, okay, and k as well. We've rewritten those in that way. And v, this guy here is the amplitude of the jth harmonic. And we're going to use this decomposition to study the stability of the solution. Now, one thing that's interesting about this decomposition is that it separates space and time, because of course I have here the exponential ij. There's all of the time, all of the space dependence is there, and the time dependence is only left here on the amplitude. And if we have a linear scheme, and this is the solution of the numerical scheme, then every single harmonic must also be a solution. Linear scheme. So this is just a sum. Therefore, if this is the solution of the linear scheme, then every single harmonic in there is also a solution. So we're going to use those things to develop the stability condition here. We can actually already write what the stability condition is going to be. The stability condition is, let's write this better. Stability condition is going to be that the amplitude of any harmonic may not grow indefinitely or indefinitely in time. May not grow as n tends to infinity, basically is what we're saying, indefinitely in time, as n tends to infinity. This is our stability condition. Okay, so now we're going to define, because we can see that the harmonics may not grow as n grows, and so we're going to define an amplification factor in terms of these amplitudes of the harmonics. And the amplification factor is defined as, call it G, the harmonic at time n plus 1, divided by the harmonic, the amplitude, at time n. So note that this is a function of the scheme parameters and not of n. It's going to be scheme parameters and also the phase angle phi, but not n. Okay? So now we can write the von Neumann stability condition, which is that G or the norm of G has to be less than 1 for all phase angles J, which are equal to J pi over N, with J between minus N and N. So let's go straight to an example. Okay, the first example is going to be the one we've already looked at with in the beginning of the class by looking at the modified equation. Now we're going to look at it from the von Neumann point of view. So let's consider central difference in space. And as before, so our scheme is un plus 1 I minus un I over delta t plus c delta c2 over 2 delta x un I plus 1 minus un I minus 1. Okay, you recognize that. We've just worked with that. So we're going to write it in explicit form. So let's take now sigma equals to c delta t over delta x, which is going to be our only parameter in the numerical scheme. And we write it in explicit. The explicit scheme now is un plus 1, our only unknown, is equal to uni minus sigma half uni plus 1 minus uni minus 1. So now we replace all the terms by a Fourier expansion. So replace all terms. This is going to be a general method. All terms of the form u n plus k. So in general, because the scheme could be any order I plus m, by the Fourier expansion v n plus k. Here's our time dependence. E to the power I plus m, phi. Phi already has the j pi over n that we had in the previous example. So now we put this on the scheme here. And we have here n plus 1. So v n plus 1 e to the power I, and we have I phi equals to v n e to the power I, capital I, imaginary number, little I index, phi, minus sigma half, and we have v n e to the power I, we have now I plus 1, phi, and we have here just I minus 1. So now we can see that we can simplify. We can divide over by this guy here all across. We simplify and we get vn plus 1 equal to vn minus vn times pi half, and we have e, here we had plus 1, so we're left with I, and that's just a 1, so phi, and minus e minus 1, so minus I phi. Okay, almost there. So now, yes, mistake?
Where did the pi come from?
Oh, it's not a pi, it's a sigma, thank you. This over here. It's just me trying to write and speak at the same time. Okay. So now we can find the amplification factor. And you see that G, which is equal to Vn plus 1 over Vn, is clearly here that we can obtain that dividing over by Vn, and we have 1 minus sigma half times, well, this we can express in terms of transcendentals now, so that's just 2I sine theta. And the halves go away, so it's 1 minus I sigma sine theta. Do I have the sigma? Yes. 1 minus, let's skip an I. No, I is there. I sigma sine theta. I'm sorry, phi. There we are. I've got it here. And now the stability, let me squeeze stability here, requires that the normal G be less than 1. So let's write G times G conjugate to get the norm. And that's going to be 1 plus sigma squared plus, because I take the square of capital I, and that just gives you minus 1. So cancels out this sign. Sigma squared sine squared phi, which you can see that it's always greater than 1. Greater or equal than 1, because this could be 0, which never satisfies stability. Yes, everyone? So we see using, this is the von Neumann method to prove that the centered scheme for the convection equation with forward difference in time is unconditionally unstable. It's useless, basically. Let's do another example. We're just gonna do examples for the rest of the class and look at them all. So, the centered scheme for convection equation with forward difference in time is unconditionally unstable. Example 2. Let's now go back to the center difference, but implicit first order difference in time. So, how do we write that? Well, we replace on the right-hand side the n's by n plus 1. We've done it so many times. I hope that you have it more or less memorized now. So un plus 1, I equals uni minus sigma halves. Like in the previous example, the only difference now is we have n plus 1 here and I plus 1 as before, un plus 1 and I minus 1 as before. So we do all the steps that we did for example 1, replace each term by the finite Fourier expansion, and we divide over. We're going to always divide over by that common term e to the capital I, small I, phi, always going to divide over by that, and we're going to get, in this case, Vn plus 1 equals Vn minus Vn, again, sigma half, and we're going to have some leftover exponentials here. One is a plus 1, and the other one is a minus 1. And so now we can get the amplification factor. Actually,
Shouldn't the second one be n plus 1?
Yes, thank you. Very much. Thank you, thank you. G equals Vn plus 1 over V. So we can just write this now. We're going to have to, well, let's do it like this. 1, we divide over this whole equation by Vn. So we're going to get G in the right-hand side and on the left. So I get 1 minus sigma half times G times the exponentials that I have in there. And now I can solve for G and get that G is equal to 1 over 1 plus I sigma sine phi. Try not to make a mistake here. There we are. So now I want to look at the norm of G squared, which is G times G conjugate, and you'll see that gives me 1 over, you can, I'm skipping some steps here, but you can see more or less this one. And since the term in the denominator has just a positive thing added to 1 all the time, 1 over that is always going to be less than 1 for all values of the angle phi, which indicates that this scheme is unconditionally stable. The only thing that we did is change the scheme from an explicit one to an implicit one with the same spatial discretization, and we turned it a useless scheme into a very useful one because this is always stable. Of course, as we've seen before, the implicit scheme is going to result in a linear system, so it's going to require more work to solve the solution because we're going to get a linear system for each time step. It's a tri-diagonal system, so it's not very hard to invert, but it's more work than the explicit one. So hopefully you're seeing something interesting in this, and let's look at yet another example. Example 3, which is going to be the forward, first order upwind scheme. So that means that we have backward difference in space, and we're going to use an explicit first order in time. So we have u n plus 1 I equal to u n I and minus sigma, our CFL number, and we have backward in time, so this one is I and this one is I minus 1. Explicit, so these two are n. So now we can skip some steps. We're going to replace by our finite Fourier series. We're going to get Vn plus 1 on the left. We're going to get Vn on the right. We divide over by Vn and we get our amplification factor, which is equal to Vn plus 1 over Vn. And that's going to be equal, you can see more or less from here, 1 minus sigma, and I'm going to have 1 minus e to the minus capital I phi. Now we have to kind of juggle a little bit these terms and move them around. We got 1 minus phi plus phi cosine. So you need to remember your and minus another term here. I hope it fits, sigma sine phi. Kind of fits. We can still manipulate this a little bit more and write it as, because what we want to see is that something definite that tells us whether this is greater than 1 or less than 1. So we can still rewrite this as 2 sigma sine square phi half in terms of the half angle. Minus another term still, which is phi sine theta, the one I had here. So now it's a little bit more complicated than before, and the trick to visualize this one is the following. We look at the real and imaginary parts of G, call them psi eta, and you see that psi, which is equal to the real part of G, is equal to 1 minus 2 sigma sine squared phi half, which you can still rewrite 1 minus sigma plus sigma cosine theta, and the imaginary part is equal to this from here minus sigma sine theta. So you have sine theta, cosine theta, both of these terms multiplied by sigma, okay? And so you can see that these sine theta, cosine theta terms on the complex plane indicate a circle. And so if you consider this as to be like two parametric equations for a curve representing G on the complex plane, with phi a parameter, then you can recognize that there's a circle here centered at a point on the real axis, at the point 1 plus sigma, sorry, minus sigma. So if I draw that, okay, if I draw that circle centered on the real axis at 1 minus sigma, it looks like this, and sigma would be the radius, and it goes around here as the parameter phi changes. It just goes around here. This is the center, 1 minus sigma. So in the complex plane, G is represented by this circle, and you can see that the stability condition requires that G is less than 1, right? So it means that the whole circle that represents G should be, so the circle for G should be inside the unit circle, which is drawn by the bigger circle over here. We want this circle to always be inside, so everything outside here is unstable, and everything inside here is stable. And therefore this circle has to be inside that, and therefore we have stability for 0 less than sigma less than 1, which means that the scheme is conditionally stable with a CFL number, with the same CFL condition that we obtained before, with CFL less than 1. Okay, now we're going to look at the same backward difference in time, but the only difference is we're going to change the time scheme from an explicit one to an implicit one. And so this is example 4. And we use an implicit first order upwind. So that one has backward difference in space. And we can write that easily now. Un plus 1 I equals Un I minus sigma, and this one has n plus 1. Now, oops, that one is we want a backward difference, so this one is just I, and this one is I minus 1. Okay, so now, as before, we put in our finite Fourier series, we divide over, and we can get G, and it's going to be 1 over 1 plus sigma 1 minus E minus I. We've done one very similar to this one a moment ago, so it shouldn't be too hard. And we can write the stability condition. G times G conjugate. We want this to be less than 1. It is actually equal to 1 minus sigma plus sigma cosine phi squared. I'm skipping all this algebra. You can check it, but it's not too hard. Sigma squared sine squared. And we want this to be less than 1. We see here that, of course, this is, well, basically always less than 1, because this term down here we're adding something that goes between 0 and 1, then subtracting. This is always positive, this is always positive, and so on. And this is for all phi. So we get that this is unconditionally stable. And you are probably seeing a pattern here. Basically, most implicit schemes are turning out to be stable, and the explicit schemes are at best conditionally stable, and sometimes unconditionally unstable, which means that they're useless for any practical, they're useful for academic purposes, to give you an example, but they're useless for any practical work. And this is the general trend. But of course, like I said before, the implicit schemes require a little bit more work per time step. Let's look at one last example. I think it's my last one. Let's see. I want to do an example with the diffusion equation. Five or six? 5, I think. So this is going to be diffusion equation with explicit first order in time and center difference in space. So our equation is du dt equal to new second derivative of second derivative of u with respect to x, and we discretize that, and we've done this for our assignment, so un plus 1 and un plus sigma delta t over delta x squared now. And we have the center difference for the second derivative, which now involves the middle point as well. So n I plus 1 minus 2 un I n plus un I minus 1. That's our center difference for the second order derivative, and we can apply the same method to obtain the amplification factor g, and it's going to be equal to 1 minus beta. Let's call all this guy, we call this, put the new, yes, we call this beta. It's our only parameter. And you have to just do a little bit of algebra to obtain this sine squared of the half angle. Stability requires that this be less than 1. And we find that this is satisfied for minus 1 less or equal 1 minus 4 beta sine squared of the half angle and less or equal to 1. Or 0 less or equal from beta less or equal 1/2. So the scheme is stable for nu greater than 0 and nu delta t over delta x squared less than 1/2. Now this is the stability of the physical problem, diffusion, and this is the stability of the scheme, basically a conditional stability. And did any of you have a diffusion equation that blew up? Okay, now you can go back and look at that and look at the choices of parameters that you had and check this, right? Von Neumann stability analysis gives us a very precise limit for the stability of this scheme. So we've seen, I had one more, so I'm not going to do that example because I'm tired now of writing all of this, and so I'm just going to tell you that if you can do the example now 6 by, you can do it yourself, changing to an implicit scheme in time, and you're going to get unconditionally stable. So, we get that explicit schemes lead, in their very best case, to conditional stability, while implicit schemes are unconditionally stable, which is great, but they require more work, as I said. Also note that stability puts a limit on the time step for a choice of discretization in space. And this limit on the time step has the physical interpretation that the solution really, you can't allow the solution to progress too rapidly in time. If you let the solution progress too rapidly in time, then this becomes a problem, especially for convection-dominated flows. Those are the cases where this is most evident. And this could become very dramatic if you have something like compressible flows where things are moving really fast. Imagine if the flow is moving at the speed of sound. If you calculate and put these things on the, with the speed of sound, c, the constant that appears there in your convection term, also is included in your CFL number. And if c is very large, like the speed of sound, it means that your delta t has to be very, very, very small, like 10 to the minus 6 or something like that. And then you're in very bad shape if you want to use one of these schemes. So basically, on the other hand, implicit schemes have no restriction on the time step. So they will be more useful for these applications. And, well, let me say that the choice between implicit and explicit schemes is a source of tremendous debate in the community up to this day. Everybody has their favorite schemes, and you can have heated discussions with people over implicit versus explicit for a variety of applications. For the diffusion equation, the explicit time step restriction, which we see here, is generally not too severe. But notice that the diffusion, the numerical diffusion, can be quite large depending on the value of your delta x. It's first order on delta x, so it could be the accuracy could be quite low. So in general, all of this stability of numerical schemes is a very well understood problem now, but remember we have made the assumption of linearity, so we've assumed that this is a linear problem. For linear problems, it's a well understood situation. And also we've neglected all the effects of boundaries, and if you have boundaries, it can get quite messy. Okay, I want to leave it here, and see you all on Thursday.